Hello everyone, I'm Rajesh Kumar Dubey and I welcome all of you in the 13th International LISA Symposium. I'm going to present my talk about Hubble's constant with gravitational wave 170817 standard siren and GW190814 dark siren. My co-author for this presentation is Dr. Shankar Pathak and we both belong to lovely professional university, India. I will start with a brief history of Hubble's constant. The graph which you see here is the original graph from 1929 data by Edwin Hubble. On the left hand side on the vertical axis, you can see the linear relationship between radial velocity, vertical axis wrongly labeled in kilometers in Hubble's original paper, and distance which is on the horizontal axis, which is labeled in parsec. The distance range only up to 2 megaparsecs, and this graph gave an overestimated value of Hubble's constant, and it's very huge as estimated in 1929, and it is equal to 500 kilometer per second per megaparsec. Now we have after that adopted so many methods for observing H0, like observations of Cepheid variables, observations of type 1a supernova, Vitali-Fisher relations using cosmic microwave background CMB, HST observations of Cepheids in the Schuster program, cosmic distance ladder, and since then from 2001 to 2016, I will discuss about Reyes et al. 2016 estimated value of 73.24 nearly, and what the biggest achievement we have gained is the reduction of the total error on H0. The graph here shows that the uncertainties in determination of H0 is being reduced considerably from year to year, and now the best estimation from Reyes L is 2.4% determination of the local value of the Hubble's constant, and it includes only systematic error for final uncertainty of 2.4%. Then cosmic microwave background gives a different result for the same cosmological constant, and again the Planck satellite result in 2018, it gives the value equals to nearly 67 km per second per megaparsec. What you see here that ranging from 2000 to 2020, we have so many different values with different error bars, with different accuracies about H0, and this is therefore has created a we can say that the values does not match, and that's why we term it as Hubble's tension. Now we have a new approach we have reached, which is the standard siren, and it is a novel approach to measure the Hubble constant, and we use gravitational waves for measuring the value of Hubble constant. There are various reasons for this. The very first one is that it is an independent measurement even without an electromagnetic counterpart, and if electromagnetic counterpart is available, it's a good thing, but even if it is not available, the values can be calculated. The collapsing neutron binaries are a great source. They emit both light and gravitational waves, and this is actually a true test of general relativity, so we can totally rely on that, and they can measure both redshift and distance simultaneously, and the redshift Z using optical telescopes, they can be measured and can be cross-checked, and the R using gravitational waves. LIGO and Virgo gravitational wave measurements of collapsing neutron star binaries and black hole neutron star binaries at cosmological distances to determine the cosmological parameters of our universe. From the observed gravitational wavefront, one can infer as direct observables the luminosity distance d of the source, and the binaries are two redshifted masses m1 dash and m2 dash, where mi are the actual masses and z lambda delta over lambda is the binaries cosmological redshift. And assuming that the neutron star mass spectrum is sharply peaked about 1.4 solar masses, so the binary pulsar and X-ray sources observations suggest that the estimation of Z should be mass of the neutron star divided by 1.4 solar masses and minus 1. The actual distance redshift relation dz for our universe is strongly dependent on its cosmological parameters. The Hubble constant h naught or h0 equal to h naught over 100 kilometer per second per megaparsec, the mean mass density rho m, or density parameter rho naught equal to 8 pi by 3 h naught square rho m, and the cosmological constant lambda or lambda naught. So by statistical study of necessarily noisy, obviously, measurement of d and z for a large number of binaries, one can reduce the cosmological parameters. So the distance is determined by gravitational waves by this relation, what you see here. And in this relation, f is the gravitational wave frequency, h is the amplitude, tau is the time scale of frequency change, and c is known numerical constant. And these equations determine r as f, h, tau all are measurable. The redshift is being determined by the optical emission, and we have a big question that where in the sky did this gravitational wave signal coming from, and we have the triangulation method for measuring the localization of the source with a typical error of 6 degree square. So 3 or 4 detectors or source galaxies and redshift can be ideal for the best localization of the good accuracy. Let me talk about the 170817 gravitational wave event, and it was the come out of mergers of two neutron stars, each dense remnant of a past supernova explosion that had been orbiting each other closely. They spiraled inward, radiating ripples in the fabric of space-time known as gravitational waves that were picked up on Earth by laser interferometer gravitational wave observatory LIGO. The neutron stars eventually collided in a massive explosion, generating final gravitational waves which were detected by LIGO and Virgo. The various fact sheets for GW170817 are shown here, you can see. And the most important facts which I would be like to put here are that the primary masses were 1.46, the secondary mass was 1.27, and the chirp mass was 1.186, and the final mass was less than 2.8. So this event was observed from the host galaxy NGC 4993, and this has been very important for measuring the host, measuring the few parameters from the host galaxies. LIGO-Virgo scientific collaboration has presented that this plot summarizing the interface on the Hubble's constant, the relative probability of different values of h naught is represented by the solid blue curve which peaks at 70 kilometer per second per megaparsec. So the dashed and dotted blue vertical lines, they represents the limits of 63.8 and 95.4% credible intervals for h naught. The vertical green and orange bands represent the constraints on h naught from two state-of-art analysis using solely electromagnetic data. The green band shows the range of value inferred from analysis of CMBR data obtained by Planck satellite. The orange band shows the range of values inferred from Schur's analysis that combines Cepheid variable and type 1a supernova data from the relatively nearby universe. The darker and lighter colored bands indicate 68.3% and 95.4% in credible intervals respectively, and it should be noted that the Planck and Schur's results are not in agreement with each other at 95.4% probability level. Gravitational waves result is, however, consistent with both the Planck and Schur's values. Marginalized posterior density of H0, which is in blue color, constraints at 1 and 2 sigma from Planck and Schur's are shown in green and orange. The maximum of a posterior value and minimal 68.3% credible interval from this is 70.0 with range of 12 plus 12 and minus 8 km per second per megaparsec. The 68.3% 1 sigma and 95.4% 2 sigma minimal credible intervals are indicated by dashed and dotted lines, as you can see. So the figure here now shows the joint constraints on H0 and the inclination of the binary neutron star system, and illustrates that there is a degeneracy between these quantities, meaning that the data assigns similar probabilities in a certain combination of H0 and inclination. It also causes the extended low probability tail of high value of H0, since the solid blue curve in the figure is essentially obtained by projecting the vertical axis, the contour plot in this figure. So the contour plot summarizing that analysis infers jointly about the value of the Hubble constant and inclination of the binary neutron star system's orbital plane. The darkest standing shows the region of highest probability, and this is because of the significant correlation between distance and inclination angle for gravitational wave sources, and the highest probability region corresponds to inclination angle close to 180 degree, indicating that GW170817 was viewed almost phased off. So it has got almost 15% of error on distance measure, and this may be due to due to combination of statistical measurement error from the noise and the detectors, instrumental collaboration uncertainties, and a geometrical factor depending upon the correlation of distance with inclination angle. So the standard Siren 190814, which I'm going to now talk about the dark siren, the gravitational wave signal GW190814 was observed during LIGO's and Virgo's third observation run on August 1409. The various parameters you can see here on this. The localization was 18.5 degrees square at 90% probability, as shown in this figure, and it is comparable to the localization of GW170817. The various parameters of this event are from the primary mass of 23.2, secondary mass of 2.59 mass ratio, and it is a good candidate for statistical cross relation method. And for a fixed reference, the Glade galaxy catalog is approximately 40% complete at the distance of GW190814 and contains 472 galaxies within the 90% posterior credible volume of GW190814. And to obtain constraints on H0, the methodology describes in Abbott et al. And the Glade catalog is used, and the range of H0 we here obtained is 75 km per second per megaparsec. So by the time what we see that H0 is being improved from time to time, and now I'm just going to conclude that the gravitational standard sirens can now provide the most significant cosmological parameters. The increase in numbers of events will increase the certainty of the observed value of H0. The different localizations of the events may be useful in deciding variations or constant values. The dark sirens are highly useful in measuring the cosmological parameters without any electromagnetic counterparts, and additional standard siren measurements from figure future gravitational waves sources will provide decision constraints of this important cosmological parameters. Lots of thanks for your time. Thank you.